Welcome back. And at the end of the last segment we left you with this stress distribution calculation, and the clue was that basically we have two parts, the top and the centre and the bottom, the top and the bottom being the same diameter and hence the same stress within each, and we says calculated under those circumstances was the clue given. So we use our force over area relationship, and a little trick of the trade here is that we have our force 1000 on the top, and on the bottom we have the area, which is pi d squared divided by 4, so that bit's on the bottom. And if we work, as we said before, in newtons and millimeters, our answer comes out to 3.18 megapascals, and that's for the stress in this part of the component. For the other part of the component, the only value that changes in the calculation here is the 20 squared becomes 10 squared, and that will give us a value of 12.7 megapascals for the stress in this region of the part shown. So we can now move on to an introduction to the stress and strain curve, and there's some details on Robert Hooke, who was the first person to observe this and write about it at the time of Newton. However, basically there's two types of material response that we see, and you saw this in the earlier lessons, certainly in the second lesson, that we can have a brittle material, which is this type of material, where no yielding tends to take place. See also that brittle materials can be stronger than ductile materials, as is the case here. A ductile material has an initial slope, and then after a point called the yield point of the material, or the elastic limit of the material, we have a flattening off of the curve as it starts to behave plastically, and this is classic ductile behaviour. Both brittle and ductile materials, in this beginning portion of the graph therefore, here and up to here, behave in what we call a linear elastic manner. So, and we say in the elastic region, for small strains, usually below 1%, and for testing purposes we use 0.1% for conservative reasons, that the stress is proportional to the strain, and the slope of the graph, stress divided by strain, is equal to the elastic modulus. We use E for the elastic modulus, which is also called the Young's modulus, after Young, who discovered this property. It is a property of the material under consideration. That is to say, just like the yield strength, the elastic modulus, again usually measured in megapascals, is a quantity of the material and actually gives a measure of the stiffness of the specific material. So for instance, medium strength mild steel has a stiffness of 200,000 megapascals, and so on. Aluminium 70,000, titanium alloys 120. Incidentally, carbon fibre is also analogous to that, about 120. And then as we get further down we see that polyamide and polyethylene are very, very flexible materials. These measurements were performed at room temperature, and as the quantity does depend on temperature to a certain extent. So we'll just look at an example of using the Young's modulus. If we know what it is for a specific material, it can help us find the displacement and hence the strain in a material if we only know what force is acted upon it. So we're going to look at this, a 25mm diameter bar which is 100 long, which is exposed to our famous, now infamous, 1000 kilonewton force. So again we have 1000 times divided by the area. So this is just the area, which is pi d squared divided by 4, to give us our stress as before, and in this case it's 2.046 megapascals. Once we have our stress, we can calculate the strain out by dividing the stress by the Young's modulus. So coming back here, we require this quantity, dividing our stress by the Young's modulus will give us the required value. In this case we see that it's 10 micrometers per meter, which is of course microstrains. To find x, we simply know that transpose our formula for strain to get the final value, in this case 1.02 or 1 micrometer for this particular force acting upon the steel bar. So the Young's modulus now allows us to find out the extension even if we can't observe it on the tensiometer. So just by way of completion, we'll go back to our 20mm diameter bar times 10, our specimen, and then the 10 diameter times 20 stress distribution, and show for each stress distribution we have a strain distribution also. So we calculated some slides ago that the stress in one part of the bar, the 20 part of the bar, was 3.18 megapascals. So we can calculate our strain now by dividing by the Young's modulus, and there we see it comes out to 15.9 microstrains. And likewise we calculated 12.7 megapascals. We now divide by our Young's modulus to find the strain of. So we can calculate the stress and the strain if we know what material it's used. That's the thing to take away from this. So we can evaluate the stress and strains in the aluminium part if an external force is applied here. Things to notice, of course, is the stress remains unchanged. We did this in an earlier session, an earlier segment, and this time we get a higher displacement, a higher strain, because of the Young's modulus being less, and hence aluminium being more flexible than the steel. And for the other part of the component, we see that we still have the same stress as in the steel component, but yet again the strain becomes a higher value, in this case 180 microstrains. If we know the value of the part, the length of each part, it's simply we multiply our microstrains by the value in meters. This is the only time we really need to use meters, it is the easiest way in which to do it is to take our microstrains and multiply by the length in meters. So the displacement when delta, and I'll come back to this in a minute, when delta of 10, that's to say the displacement at this point would be a value of 1.8 micrometers, while at the end of the 20 section here we'd expect a value of 2.4, which should be added of course to the 10 to give you the total displacement. So we've now got the axial loading example here, and we've started to use the Greek letter delta for displacement rather than the x value, as we said that for strain distributions and the displacement will be a function of the x coordinate. So we'll just now come back to have a look at another example, and we're going to leave you to calculate this one yourself. No strain values to work out here, just a stress value in each of the in two different types of rod scenarios. So if you could calculate this out for us and then come back to us in the next segment.